There's an announcement. Participants of session 5, Petrology, Analytical and Field Geology, please submit your PPTs to the registration desk or the announcement desk.
Good morning to all. I am Anju Maria Joseph, PhD scholar in University of Madras. My topic is assessment of microplastic interaction with trace metals and sediment texture on the basis of studies in Periyar and Pamba River in Kerala. Microbe of plastic, often less than 5 millimeter in size and originate by the breakdown of large particles. Microplastic are considered as the major environmental pollutant because its widespread availability in air, water and the sediments. Both the sediments and microplastic follows the same pattern of transportation and deposition. So we can easily predict the distribution of microplastics on the base of the sediment data. The aging of microplastic results in the alteration in its structure and certain properties like its surface area and surface charge. So it increases the interaction with the trace metals. So the combined effect of the trace metals and microplastics causes very environmental issues leading to toxic effect in plants, animals and human beings. The objectives of my study is to analyze the concentration, the morphological parameters and polymer type of microplastic in Pamba and Periyar River Basin, and to evaluate how the concentration of microplastic change with the grain size and hydrodynamic conditions, and to assess the possible interaction between the microplastic and trace metals, and to calculate the pollution load index posed by microplastic and trace metals in the environment. My study area is Pamba and Periyar River. Both are the major rivers in Kerala. Periyar is the longest river in Kerala, and both this river originate from the from Western Ghats and empties into the Vembanad Lake. Before it drains into Vembanad Lake, Periyar River reaches to the northern portion of the Vembanad Lake. Before reaching to Vembanad Lake, it flows through the industrial and commercial areas. While Pamba River joins to the southern portion of the Vembanad Lake, before reaching the lake, it flows to the agricultural area like Kuttanad region in Kerala. After the sample collection and pre-treatment, first I conducted the textural analysis of sediments using pipette method for the identification of sand-silt clay ratio and the hydrodynamic environmental condition. Then I conducted the microplastic analysis of sediments for the quantification and the identification of size, shape and color using microscope. Then the polymer identification of microplastic conducted using Raman spectroscopy. Finally, the trace metal analysis of both sediments and microplastic conducted using AS method. Then the statistical analysis, pollution load index calculation, and finally reached to the conclusion. Based on the textural classification of Shepherd, most of the sediments from Periyar River falls under the sandy classification, and the sediments from Pamba River falls under clay sand and sandy clay classification, indicate the higher concentration of clay in Pamba River. Then based on hydrodynamic environmental studies, the sandy nature of the sediments from Periyar River indicate its deposition under very violent condition, very high hydrodynamic environmental condition, and the higher clay content in Pamba River indicates the deposition under calm environment, low hydrodynamic energy condition. Microplastic of various size, colors, polymer types and shapes like fibers, fragments and films were obtained from the study area. These are the microscopic images of microplastic from the study area. we can see a linkage between the microplastic concentration and grain size. In Pamba river, the mean abundance of microplastic is about 998 particles per kg, and in Periyar river it is about 862 particles per kg. It indicates that there is a the microplastic concentration and grain size are inversely related to each other. The abundance of microplastic decreases with the increase of grain size. The finer sediments like clay tends to accumulate more microplastic due to its absorption capacity, and this pattern also highlights the tendency of microplastic to settle under low hydrodynamic energy conditions. Based on the shape classification, in Periyar river, the concentration of fibers are in Periyar river the concentration of fragments are higher, followed by fibers and films. But in Pamba river, the concentration of fibers is higher compared to fragments and films. From the graph, it is clear that we can see the linkage between the microplastic shape and grain size. The concentration of microplastic fibers is higher in clayey sediments, like fine sediments, and the concentration decrease with the increase of grain size, and the evidence of the concentration of fragments is higher in sandy sediments. This is because the fine grained sediments has higher surface area and absorption capacity, so they can easily attract and bind the fibers. Due to its denser and more irregular texture of fragments, they can easily settle among the grain size particles. With the help of the size of microplastic, we can identify the source of pollution. Is it near or away from the polluted region? The coarse and dense microplastic tends to settle near the source of pollution, and while the finer and lighter particles suspended forms and travel long distance before its settlement. In Periyar river, the majority of the microplastic collected from the Periyar river are greater than 3000 micromillimeter in size. They are large particles, indicates the direct pollution near to the river region. And in Pamba river, the concentration of fine grained sediments, fine grained particles less than 100 micrometer is higher, indicate the source is much distance from the it is come through the transportation of pollutants from far distance. With the help of Raman spectroscopy analysis and Raman peaks, 6 different types of polymer types were identified from the study area: polypropylene, polyethylene, polystyrene, polyamide, PET and PVC. In Periyar river, the concentration of polystyrene is higher. It the main source for the possible sources of the polystyrene is industrial discharge, improper disposal and littering of single-use plastic particles into the river. Polystyrene microplastic are formed by the breakdown of plastic packaging materials like box, bottles, cups, plates, etc. In case of Pamba river, we know that it is flows through the Kuttanad region, the agricultural region. Here the concentration of polyethylene is higher. The polyethylene is main in Kuttanad region. The plastic sacks which is used to construct the bunds to prevent the flow of water to the paddy field. So over time these sacks break down into microplastic, and in Kuttanad region, in Pamba river, the frequent flooding are common. The frequent flooding and the flow of water results in the spreading of polyethylene polymer microplastic to the Pamba river. The trace metal analysis indicates the sediment quality guideline proposed by US EPA for trace metal concentration shows Periyar River is highly polluted by lead, cadmium and chromium, and moderately polluted by copper and zinc. In case of Pamba River, it is highly polluted by chromium and very less polluted by cadmium. We can see a correlation between the polymer type and trace metal concentration. The microplastic polymers such as PVC, polystyrene and polypropylene show this microplastic absorb more trace metals. This is because this PVC, polystyrene and polypropylene are rough and cracked. They have rough and cracked surface and large pore spaces. Due to this reason, they attract more metals, and the concentration of metals increase along with the concentration of this kind of polymers. PET shows comparatively low absorption to trace metals. Based on the microplastic and trace metal correlation analysis indicates the area with a higher concentration of microplastic indicates the area with a high concentration of microplastic shows higher concentration of trace metals. Both they are positively correlated to each other, and the microplastic can act as a carrier for trace metals in the environment. Pollution load index is one of the best method to determine the pollution and ecological risk for the environment due to the microplastic and trace metals. Based on the pollution load index study, the Periyar River is highly polluted by both trace metals and microplastic, and the Pamba River is highly polluted by the concentration of microplastic. While comparing these both rivers, Periyar and Pamba River, the positive correlation of microplastic and trace metals are unclear, because in Pamba River the concentration of microplastic is higher, but in Periyar River the concentration of trace metals are here. Major finding is both the microplastic act as a carriers of trace metals in aquatic environment. Microplastics such as PVC, polystyrene and polypropylene exhibit higher absorption capacity to trace metals. In Periyar River, the pollution of in Periyar River the pollution of is very high due to both microplastic and trace metals. But in Pamba River, the concentration of microplastic is higher due to its clay texture, and both the combined effect of trace metals and microplastic highly affected the ecosystem of these regions. Yes, yes. Yes, yes. And agricultural related. Yes. Yes. I am trying to express how the microplastic, why Pamba river is a less polluted area, but there we can see higher concentration of microplastic than Periyar river. So this higher concentration of microplastic in Pamba, less polluted Pamba region, we can see higher concentration of microplastic than Periyar region, Periyar river. This is mainly due to the effect of and the sandy, the clay texture of Pamba river. The clay can accumulate. Yes, yes. Micro. Yes, yes. Okay. Yes. Art. Okay. Yes, yes. 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 Yes, 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 ma'am. But now only I added only this pollution load index only. Yes. In my other works, I already added all other pollution load indexes related to polymer index. Yes, I done all that indexes. Okay. Thanks.
Thank you, Ms. Sanju Maria Joseph. Now we have Ms. Arya Jain with her presentation.
ID card. Hello. I start now?
Good morning, all. I am Arya Jain, research scholar, Department of Geology, University of Kerala, and my topic is nanomaterial characterization of reddish slime material. Reddish slime material from a tropical freshwater ecosystem. And my contents include introduction, study area, methods employed, result, and implication and conclusion. So, moving to the introduction. There are many geoanthropogenic and geochemical contaminants contributed to our groundwater, and one of the main contamination is iron. Actually, iron is an essential element for human body, but when its concentration become beyond 0.3 mg per liter as per the BAS limit, it is termed to be iron contamination. And laterite is a widespread geology in the tropical areas, and which is a composite of both iron and aluminum hydroxide with clay minerals, and they contribute normally iron to the groundwater. So this iron can be in two forms in groundwater, that is Fe2 plus ferrous forms and Fe3 plus ferric forms. These Fe2 plus forms are soluble in water and the water will appear to be clear. But when it comes in contact with oxygen, it will oxidize to form Fe3 plus ions that will form a precipitate of reddish brown color. And this is acted by the iron bacteria to form a oily appearance in the water that you may see. There are so many studies about this iron contamination in groundwater, but there is no clear study about the nature of these iron contaminants present in groundwater is provided. So this is a novel study on the iron contaminants in groundwater. This is my study area, the Haimavati pond of Trivandrum district in southern Kerala. And I have collected the samples, you can see in the figure B, that is the oily appearance on the water surface. I have collected these samples, then dried it and powdered to form for various analyses. The methods include ICP-MS, XR of XPS, SEM-EDAX, FE-SEM, XRD, LRS, and BET. Moving to the results. So I have conducted ICP-MS and I got the result as 3.65 ppm of iron in my groundwater sample. Now moving to the XRF analysis. So 1 gram of dried powdered reddish slime material was taken for XRF analysis, and the sample and the results are shown in the table below. And the iron oxide value was 79.87% with a less percentage of other oxides. Now moving to the XPS analysis. The figure 2 shows the photoelectron spectra of oxygen, nitrogen, silicon, iron, calcium with the given atomic percentages. So in order to know the state of iron present, I have deconvoluted the Fe2P peak into 3 peaks, and they were obtained at 710.17 electron volt, 711.19 electron volt, and 713.46 electron volt, and they are octagonal Fe2 plus, octagonal Fe3 plus, and tetragonal Fe3 plus form. I also calculated the atomic percentage of Fe3 plus ion as 92.91%. And the fourth figure is a confirmation of Fe3 plus, that is the satellite peaks. And the satellite peaks are located at 8 electron volt distance from the major peak. Now the SEM-EDAX analysis. So the figure 5 shows the same images of the immediately dried brown material, and this shows that there are many lamella or rod-like structures in the sample. And the figure 6 shows the same images of the reddish brown slime material which were dried at an optimal temperature for a week. And I could analyze that there were many shiny flat flakes in the sample. So I conducted the EDX also to know the elemental percentages, so that I can identify that the percentage of iron in the lamellar structures were more than that of the shiny flat flakes. And also, apart from this iron element, arsenic, nickel, and chromium were also present. Now, FE-SEM analysis. To know more about the from this figure you can see that the rod-like structures have a diameter of 1 micrometer, but they have many microspheres attached on their surface. That is about 200 nanometer shell thickness. But when we consider an individual material or an individual particle, its size was ranging from 14.97 to 61.3 nanometer with an average 33 nanometers. That is, it is a nano material, I think. Okay, so I go for Raman spectra and XRD analysis. From the first figure shows the Raman spectra of the sample and at an excitation wavelength of 785 nanometer. And the high intensity major peaks were formed at 207 centimeter raised to minus 1 and 464 centimeter raised to minus 1 wavelength which corresponds to the FeO vibration. Also, my material has a seasonal fluctuating characteristic that fluctuates between the crystalline and amorphous nature. This is identified by the figure 11. That is, the Raman spectra and XRD do not show any prominent peaks. That is why it is showing a amorphous character also. Now, this is the XRD matching. From this XRD matching, we can identify that the peaks corresponds to both ferric arsenate as well as the hematite material. Also, in order to characterize the nanomaterial, I want to calculate the average crystal size. So, from the Scherer equation, I have calculated the average crystal size to be 23.8 nanometer, which is consistent with the FESM analysis. Also, both laser Raman spectroscopy and XRD confirm that my sample is hematite. So, the iron contaminant the contaminant we earliest point out was the hematite nanomaterial. Today, in water purification, we are using the synthesized hematite nanomaterials with a high absorbance capability. So, I want to test whether what is my absorbance capability on surface area of my sample. So that I go for the BET analysis, the Bronner-Emmett teller. From this analysis, I determined using nitrogen adsorption desorption studies, and from this study, I could identify that the surface area was 48.445 meter square per gram. That is much more than the synthesized hematite nanomaterials. Also, the type 3 isotherm with no prominent hysteresis loop suggests that they have multiple adsorption on the surface of this nanoparticle. And the figure 14 shows the BJH plot, which shows that the particles have a mesoporous structure. Now, implications. So, the presence of iron contamination in the water bodies of tropical regions is now a significant concern. And in tropical regions, particularly in Kerala and South India, were characterized by these widespread laterites which contribute more iron contaminants to the groundwater. From my multi-proxy investigation through different analytical techniques, I could prove that the sample identified in the reddish brown slime was hematite nanomaterial. Also, I could understand the surface area was 48.45 meters square per gram, and with an average pore size of 2.47 nanometer and volume of 5.99 cc per gram, which indicates that they have a high adsorption capability. That is, it can be used to remove the heavy metals from the groundwater. Also, in many water treatment plants and in the water purification systems. Also, it could remove the organic compounds and certain microbes like E. coli bacteria. And this is a natural and easily available form of hematite that surpass all the tedious effort to create the synthetic hematite nanomaterials. Conclusion. Our comprehensive analysis utilizing advanced analytical techniques has identified the reddish brown slime as promising natural hematite nanoparticles with unique mesoporous characteristics. And these nanoparticles exhibit an impressive surface area, efficient heavy metal absorption capabilities, and a notable absence of hysteresis in the BET isotherm, highlighting their promising potential for water purification application. And this research not only expands our understanding of natural hematite nanoparticle, but also opens avenues for innovative and eco-friendly technologies in the crucial domain of water quality management. Thank you. Thank you, sir. Yes, sir. Yes, sir. 10 minutes. Sir, actually, hematite nanoparticles are having these rod shapes. Yes. I think if, more on the structures, chemistry in the chemistry manner, then they are mostly aligning in this rod form. Yes, sir. But in some seasons, they can also form spherical structures also. That is why I say normally it will form a rod-like structures. Sir, what's sir? Sir, beyond 0.3 to 1, it is contaminant. It is contaminant. Normally it is 0.3 to 1. It's accepted. Okay. Yes, sir. Sir, actually, this oily appearance is caused due to bacteria. Whenever there is iron in water, it just if it is soluble, it just appears clear. We can't see if there is any iron contamination. But when it is acted by bacteria also, you can see this oily appearance. Somewhat you can see in the wells also. Yes, sir. Okay. Yes, sir. Yes. We are considering this as contaminant, but this has this useful thing also. Used as, yes, sir. We can use this instead of, sir. This was a sudden or a accidental discovery. Actually, I just used some methods like searing, etc. for collecting the sample, but I can't. At last I used banana leaves, and this particle correctly stick on the banana leaf, and I can dry it, and they came out as flakes, and then these are powdered and used for various analysis. Can we? Yes, sir. Sir, yes, if the iron content in the water is more, when it is actually depend on seasons. If it is rainy season, we can't get this sample. It needs some sunlight also. Then only it can make thicker form. Actually, this in the sunlight only we can get the thicker form of this material. No, no, no. Summer only you can get it. Okay, sir. Yes, iron oxide. From Fe3 plus. Yes, sir. Yes. Sir, actually, okay. Yes, yes.
Thank you, Ms. Arya. Thank you, Dr. D. Padmlal, for chairing the session. I request Ms. Shreya Mondal to submit your PPT at the registration desk. Shreya Mondal, please submit your PPT at the registration desk. Next, moving to the session 5, Petrology, Analytical and Field Geology. The first speaker is Dr. Prabhagar Naraga from IIT Bombay, who will present on late Paleoproterozoic granite magmatism in the South Central Satmada Complex, Aravalli Craton, Northwest India. Structures, geochronology and tectonic implications. I invite Ms. Alana Maria Koshi to give a brief introduction about our esteemed speaker.
I consider it as an honor bestowed on me to introduce our next speaker, Dr. Prabhagar Naraga, Associate Professor in the Department of Earth Science at IIT Bombay. He has a career marked by excellence in both teaching and research, an expert in metamorphic petrology, tectonics, and electron microbeam analysis. Dr. Prabhagar's work is centered on unraveling the complexities of Earth's geologic process. His research interests include the fundamental mechanisms of metamorphism and metamorphic phase equilibria. Additionally, he has also contributed significantly to the understanding of the Archean crustal evolution, Proterozoic mobile beds, and deformation microstructures. Dr. Prabhagar completed his PhD in metamorphic petrology and tectonics from the Indian Institute of Technology, IIT Kharagpur, in 2013, following his MSc in geology from Pondicherry University, where he was a gold medalist. His accolades include the prestigious INSA Medal for Young Scientists in 2020 and the SERB Fast Track Young Scientist Award in 2014, and many more. With over 25 publications in reputed journals and a H-index of 9 and more than 300 citations, his scholarly contributions have advanced the field of geology and petrology. Dr. Prabhakar's leadership, combined with his passion for research and teaching, continues to make a profound interest and impact on the academic and scientific community, inspiring young students and researchers. It's a great pleasure to have you with us today, sir. Now, I humbly request Dr. Prabhagar Naraga to proceed with his session. Over to you, sir.
Yeah, thank you. Thank you for the nice introduction. So, yeah, so I'm happy to be back here after a long time. So I thank Dr. Linto for inviting me here for giving this talk, and I'm also associated with some of the students and guiding some of the students from this college at IIT Bombay through internship programs. So I'm happy to share my work in this presentation. Can you share the presentation? Yeah. Okay, it doesn't show the, I cannot show the pointer here. But it doesn't show on this screen. No, it doesn't show, I think. Yeah, it doesn't work on the screen, yeah. Okay. Okay, so I think it's, okay, fine. I can use this pointer instead of this one, yeah, okay. Okay, good morning everyone. So I think this is a bit change from your talks you have been hearing from yesterday. So I'm going to talk about the late Paleoproterozoic granite magmatism in the South Central Sandmatha complex, Aravalli Craton. So I will be talking about the structures, geochronology, and tectonic implications. Oh, okay. I'm not sure it will not reach here, so it's okay, fine. Thank you. so I'll start with this slide. So you can see that this is a general scenario of a subduction setting. So where you can see that there is extensive continental growth, and this continental growth is initiated in the Paleoproterozoic time when you have a crustal thickening. So the Archean to Proterozoic transition is driven by this transition from the vertical tectonics to the horizontal tectonics. So where you can see this, the crustal thickening is one of the major phenomena. At the same time, can I go on this side? Yeah. So I think it's better I talk from here. So when you see in this slide, so you can see that you have a crustal thickening. At the same time, you have the rocks are being exhumed. So when there is exhumation, you are going to expose the deep crustal parts, including the granulate facies rocks as well as the magmatic rocks. So often you will find in these orogenic belts the associations of the granite and granulate belts. So now you can also see that there is a global event at 2.1 to 1.8 where it involves the amalgamation of the Columbia supercontinent, and this Columbia supercontinent amalgamation has led to some of the associations of the granites and granulate belts. So in the globally you have the records of this granite granulate belts. In Indian scenario, you have the San Mata complex, which is situated in this region. It has the records of the granite granulate associations of Paleoproterozoic age. So coming to the Aravalli Craton, it is a very complex, it is having very complex geology, and you have several theories existed about the classification. I don't want to go for the classifications, but I have given you the simplified geology of the region. So what you see here is, this is the oldest rock, and here you have Archean rocks from 3.3 to 2.5. This is known as banded gneissic complex, and this part is called as San Mata complex, and this is also known as a reworked basement and equivalent to this one. However, the ages that you find, they are mostly of very sporadic ages of 2.5, and largely you will find 1.7 to 1.8 is the age of this complex. Surrounding that, you have a Aravalli supergroup of rocks which are metasedimentary rocks formed due to the Aravalli orogeny. In the western part, you have the Dilli supergroup of rocks, again metasedimentary rocks formed due to the Dilli orogeny. The age of the Aravalli orogeny is about 1.8, they are Paleoproterozoic, whereas the Dilli supergroup of rocks and Dilli orogeny formed at Paleoproterozoic to the Neoproterozoic. So they have a transition in the Dilli supergroup of rocks. Now if you look at the San Mata complex, it's very interesting that you can see that there are several granitoid bodies within the San Mata complex, here the yellow region, and in the neighboring regions also you can find several magmatic bodies. More interestingly, what you can see is that all the ages, if you see reported ages, they are from 1.7 to 1.8. So you can see that there is a large scale magmatism occurred in the western part of the San Mata complex. So this gives us the opportunity to understand the crustal evolution, especially belongs to the Proterozoic time, and in association with the granites and granulites. So these are the two regions which I have focused for understanding the granite and gneissic associations and their relationships. So these are the detailed maps of these granitoids. You can see this is a name known as the Gyangar granitoid, and this is called a Amet granitoid. If you look at this outcrop pattern of the gneisses itself, the granites, the body itself is elongated. You can see that there is a stretching on this direction, stretching on this direction. The outcrop pattern itself is deformed. So it shows that there is a large scale deformation is happening for the granitoids. Now you can understand the granitoids in two ways. One is the crustal evolution point of view. In crustal evolution, you have to look for the isotopic signatures as well as the geochemistry and talk about the petrogenesis and their source and source characteristics. Secondly, you can also talk about tectonic evolution, because the granites are the marker bands which respond to the deformation, so they can fold, they can show multiple deformations. So my interest here is to understand the deformation point of view rather than a isotopic point of view. So I show you some of the interesting structures that you find in the gneisses as well as the granites, because the granites are intrusive into the gneisses. So you need to understand both the gneisses and granites together to understand what is happening in this region. So first I will talk about the gneisses in which the granites are intrusive. So you can see the gneisses overall, they show 3 deformation features. You can see that some of the images are, I think, not focused. You can see that there is a recumbent fold here, and the gneisses shows the recumbent fold. The sketch you can see that, and the actual plane of the recumbent fold is the S2 foliation. So you have a S1 and S2 foliation, and both together are co-folded to give rise to S3 foliation. So basically it is a hook-shaped fold. The hook-shaped fold is a type 3 interference pattern in when you look at the fold interference patterns. So overall, in the gneisses, you find there are 3 fabrics, and all the 3 fabrics are interconnected. Now when you come to the granites, the granite has the S1 foliation, and if you see the recumbent folding in the gneisses, so the recumbent folding in the gneisses has actual planar fabric, and that fabric is common to the granite. So it tells you that the granite is emplaced after the formation of a early foliation in the gneisses, which you can see in the top part. And this is a close-up view of the granite, where you can see that there is a large porphyrophenocryst which has been deformed, and this gives you the shear sense of a sinistral sense of shearing. At the same time, you can see the foliation is a flat. So the early foliation that you find in the granite is a flat foliation. Now what happens to this foliation later? You can see that this foliation has been transposed, it has been folded, and it gives rise to upright folds, and you have actual planar fabric is S2. Now you can also see that the lineation that you develop during the S1 foliation is a melanitic fabric that is also folded during the D2 deformation. So this gives rise to that the early lineations and foliations has been folded by the later deformation events. So this is also showing you the relationship between the S1 and S2, and the section view of this S2 shows there is a normal sense of shear based on the orientation of the phenocryst. Now this is an interesting thing, that followed by S1 and S2 you have a S3 foliation. This is a third deformation. Now how do you identify the third deformation? The orientation of the axial planar fabric. It is different from the S2 foliation. S2 is northeast southwest trending striking foliation, whereas S3 is a north-south striking foliation. So obviously when S3 is forming, it is going to affect both S1 and S2. So the superimposition of S1 and S3 gives rise to upright folds because S1 is a flat foliation. However, the superimposition of S3 and S2 gives rise to a reclined fold. So one fold is like this, the another fold is like this, where you have a fold axis is vertical. So this is a relationship that you can see from the S1, S2, S3 of the granite. Now this is a very complex diagram, looks complex, but what you see is that right now I have this S1, S2, S3 are the foliations, and I have the lineations. F1, F2 are the fold axis, and you have the stretching lineations. Now if you see that, the summary is I have a S1 foliation which is a flat, which is folded. It has a SL1 stretching lineation. Now this is folded to give rise to, yeah, no problem. Okay. So S1 foliation is folded, upright folds, and this has developed the SL2 foliation, SL2 lineations. Now later you have a S3 foliation, which is affecting both S2 as well as S1. So this complete picture gives you the interrelationship between the S1, S2, S3, that is the 3 deformation fabrics, and the orientations of the different lineations and the fold axis. So this is the summary, same summary is mentioned here. So Now what is the next step? The next step is to understand the deformation features. So to understand the deformation features, you have several techniques. The first, you start with the microscopic observations. So you have seen the mesoscopic observations now. Now you move forward to the microscopic observations. So what do you see in the microscopic observations? You have to understand the vorticity of deformation. So if you are not aware of the vorticity of the deformation, the vorticity of deformation is talking about the component of the pure shear and simple shear. I hope you know about the pure shear and simple shear. The pure shear is the stress acting orthogonal to the surface, whereas the simple shear, the stress is acting parallel to the surface. So what we need to see in the vorticity analysis is what is the combination of the pure shear and simple shear. So for example, if I have a pure shear only, my stress is acting like this. If I have a simple shear, its stress is acting like this. Now if I have a combination of this, so it is acting pure shear then simple shear. So my vorticity is in this direction. That is the mean moment vorticity. Similarly, I can also have a pure shear and simple shear in this direction. So my mean vorticity is in this direction. So to understand the vorticity analysis, we need to do the deformation. We need to cut the section in a specific orientation. So this x, y, z are the orientations of this strain axis. So without confusing you, so I will simply say that the xy is the foliation plane and x is indicating the lineation direction. So I have to cut the sections orthogonal to the foliation and containing the lineation. So this is my foliation, this is my foliation, and I have the lineation like this. So I have to cut the section in this direction, that is called xz section. So you take the xz section and prepare a thin section and to understand the deformation mechanism. And why do you cut the xz section? Because xz section is the one where you find the maximum deformation. So you will find the various deformation features more effectively in the xz section. Now coming to the microscopic observations, so these xz sections you prepare thin section and you have to observe under the microscope. So what does it tell you? So when you look at under the microscope, in addition to the mineralogy, you also have to look at what is the orientation or movement mean shear orientation. So here in this case, you can use SC fabric. The SC fabric in the sense, this is C fabric, and you can see this is the S fabric. So SC and C prime, you have another fabric called C prime fabric. So all these three fabrics are used to understand the shearing direction. So here it shows top to the southwest direction. It is the same thing in two different sections, but in this section it shows top to the west direction. So overall, there is a movement towards the west and southwest direction in the region. So now apart from that, now you are going for the vorticity analysis. In the vorticity analysis, you have to use the slabs which are cut orthogonal to along the xz plane, and in that we have to mark the different porphyroclasts. Okay, these porphyroclasts are nothing but these are the previous phenocrysts in the granite which are deformed and formed as organs. Now you need to understand that here you have to measure some of the parameters from this slab. So one is that you have to measure the long axis, you have to measure the short axis, and also you have to measure the angle between the long axis with respect to the foliation, that is called theta. So we use aspect ratio, the long axis by short axis, and the theta values to understand what is the mean kinematic vorticity number. So that is a mean kinematic vorticity number is given by different authors. There are different methods. So one of the method is the porphyroclast aspect ratio method, where this is a formula is being used. The second one is rigid grain net analysis, where this is the formula being used. This is only given for information. So I'm going straight away moving to the results. So what does this results tells me? The PAR method as well as RGN method gives me some numbers of mean vorticity numbers. These numbers. So what are these mean vorticity numbers? Where I'm using in this plot, and when I plotted here, I can see that this is a pure shear dominated regime and this is a simple shear dominated regime. So our samples are plotting in this region which is falling in the general shear, where you have a combination of both pure shear as well as a simple shear. However, in most of the cases you have a pure shear dominated regime. That's what you can see from here. But however, this method has some disadvantages because you are using a specific number of clasts. You are not using a large number of clasts. Therefore, it becomes a problematic whether your strain analysis is correct or not. So for that, this can be used now using some of the emerging method, like the conference is also on emerging methods. So I can show you this slide just to give an idea about that. I can also improve my vorticity analysis by using this electron backscatter diffraction technique, and this is a simple technique, but it's very complicated. How? You need to attach this attachment of the EBSD detector to the SEM, and this gives you a lot of information. What kind of information? It will give you basically the crystallographic orientations of the minerals, and based on the crystallographic orientations you can also find whether the crystals are oriented in a preferred orientation or not due to the deformation. At the same time, you can also look at what are the different kinds of deformation mechanisms. You would have heard about subgrain rotation, recrystallization, dynamic recrystallization. So all these features you can identify using this technique. To make you understand, I give you this slide. You can see that this is a phase map where you can see this is a simply plagioclase. This is the X-ray element map where you can see plagioclase, and this is quartz. Same map when I run using the EBSD, it looks completely different. Why? We are plotting the poles of the crystallographic axis here. It shows there are different very small grains you can see here. That means this is a kind of a shear zone where you have a large scale grain size reduction has occurred from large phenocryst to the small grains. Now why you have different colors? All these different colors says there is a different angle in the different grains. Like for example, the grains are, one grain is like this, the another grain is like this, or another grain is like this. So you have a different orientations of the crystallographic axis. You can also visualize this in this image, where you can see that the feldspar shows there is a large scale angular difference in terms of a deformation. So, and this is you can visualize in this way. You can see that the A axis is in this direction, here A axis is in this direction, C axis is towards the top, and here is towards the bottom. So these kind of orientations will be known from the EBSD analysis. At the same time, the quartz is extensively studied using EBSD. In quartz, you can see if I find this kind of a pole figure, and this pole figure will tell me what is the temperature of deformation. So if I have a low temperature, I will have a features like this. If I have a high temperature, I will have a features like this. But basically, what is the indication of this? Quartz will have a slip and C slip. In quartz crystallographic axis, you will have a slip along the A axis, and you can also have a slip along the C axis. So A axis slip occurs at the low temperature, indicated by these features. C slip occurs at the high temperature and indicated by these features. So we applied this method to the rocks which I showed you just now, especially for the zones where you have a S1 foliation and S2 foliation. So when I apply for the S1 foliation, you can see that here in the petrographically I got top to the southwest direction, and you can see that I got the cluster of the poles, and which are again showing you the top to the southwest. So my strain analysis, which was done based on the limited data set, is also matching with the EBSD study, where the pole data shows the similar orientation but low temperature deformation. And same thing with the S2 foliation. The S2 foliation is also showing the top to the west orientation, and the EBSD data is showing you the same information. And you can also look at the grain angle difference between the different grains. Now moving ahead, so we have seen the deformation, we have seen the microscopic observations. Then we need to understand what is the timing of this emplacement, what is the timing of deformation. For the timing of emplacement, we obviously go for the zircon dating, where we can it is done with the LAICPMS, and you get the dates here is about 1.8 is the highest peak that we got. So 1.8 is considered as the timing of the crystallization. However, there are some lower intercept values which is about 800 million years. Now we will see what is the meaning of this. Secondly, we have also used monazite dating. The monazite dating is one of the robust technique where you can perform the in situ analysis, in situ dating. That means in zircon you have to separate the grains, but in monazite you can use the direct thin section and analyze. And this is done with the electron microprobe. So in the electron microprobe, if you have a monazite, you can date that. And monazite is a Re bearing phase phosphate. It has good amount of uranium and thorium. Now the interesting part with the monazite is the monazite can recrystallize due to the deformation. For example, here I show you because of this folding, and here you have some shearing. Due to that, you can see that the monazite can recrystallize and it will develop the recrystallized pressure shadows. Now if the monazite is having this kind of information, if you date these different zones, you will get the different dates, and that is also giving you the timing of deformation. I'm not aware of any other technique where you can date the deformation. This is one of the efficient technique which I have experienced. So now with this technique, what we see in the granites that we have studied is that you can see that the core, I think the number is very small, the font size is small, but you can see that it is a 1.8. This core is 1.8. Here you have a rim of 1.7, and this part is 950 to 990. So this Younger event is exclusively forming the same example which I showed in the previous slide. It is giving you the same scenario. I have a 1.8 core and the rim is about 900. So this tells me about the timing of the deformation. So overall, if I summarize the things from the deformation structures and the date, so what we can say is that the granitoids are the paleoproterozoic in age, and they are classified as monjogranites. This is a geochemical information which I have not shown here, and they are megacrystic in nature because they have a very large phenocryst. They were emplaced during the Aravalli orogeny because this is matching with the timing of the Aravalli orogeny, and that is also roughly matching with the Columbia assembly. And after the emplacement, what we have seen is the early foliation, the S1 foliation, which has developed in these granites, and followed by you have a northeast southwest directed shearing, and this shearing is occurred at two times. One is at 1.73, other one is at 0.93. So there is a large gap in the deformation. So you have a emplacement, early myelinization S1, then you have a late myelinization around 900 million years. So that is, so one is about the Aravalli orogeny closure, the second one is about the Delhi orogeny closure. So in terms of pure shear and simple shear, so it is the granitoids has mostly deformed by the pure shear dominated regime, and most importantly the granites have recorded the episodes of two major orogenies in the Aravalli craton. So although I am using the term Aravalli craton, the part which I studied is falling in the orogenic belt where you have a large scale crustal thickening has occurred. And this is a kinematic diagram where this earlier myelinization, you can see 1.73 deformation and the 0.93 and 90 deformation. And these are the different shear patterns and orientations of the fabrics that you can see simultaneously in this rock. So from this, what we can say is that the granitoids gives a information about the not only the crust evolution point of view, it also talks about the tectonic evolution point of view and what kind of shear kinematics has played a role in the Proterozoic time. So this is one of the example that we have studied during our work. Thank you. you have any questions? Yes. Yeah. Yeah.
Uh, uh, I have not done hard rock geology, so question may be silly actually, but you can just try to answer that. Because you started off with the diagram showing plate tectonics, ended up with Columbia assembly and the time frame with zircon dating.
Yeah.
Can you put this in perspective of the plate tectonic history of the Rodinia supercontinent? Can we do that in India?
Rodinia supercontinent.
Yeah.
So the Rodinia supercontinent age is about 1.0.
Yeah.
So the latest event that I have reported, that is 900 to 1000 million years. This is overlapping with the Rodinia assembly event.
Yeah.
So we have, so as I said, the Columbia is one episode that is recorded, well documented in this area, and this Rodinia assembly event is also documented, but not well documented, well preserved in this region.
Yeah, that is what I meant
But
to
we
say.
have a
So this is a introduction to mineral physics with some of my studies as example. So this is just a introduction to myself. So I'm currently working at Institute for Planetary Materials, Okayama University, Japan. So I work on several topics starting from ultra high pressure temperature experiments to numerical modeling of geodynamo. So this is some introduction. So so as we know that the Earth is divided into the interior is divided into several layers. So the basic one is, for example, crust, mantle, and the core. So these the classification is completely based on chemistry of these layers. But not only that, we have further classification: lithosphere, asthenosphere, and upper mantle. So within upper mantle, you have transition zone, and then lower mantle. And most recent discovery in the lower mantle is D double prime layer, and then outer core and inner core. So these are not based on the chemistry alone. So this is mainly based on the rheology or the physical properties of the each layer. So how we get the information from interior of the Earth? So there are indirect methods, that is seismology. Then the seismic velocity depends upon the density of the medium in which they are propagating, and also the elastic properties such as the rigidity modulus and the bulk modulus. So if you have velocity variation, then you can detect the density variations in the interior. At the same time, you can also, from the travel time relations, you can calculate how thick the layers. And there are some direct methods, that is the magmas. So sometimes the magmas coming from the shallower depth, and sometimes it's come from deep. So the most common example is the deep plumes. As you know, the Hawaiian horseboat is believed to be comes from the deep mantle. So this gives some idea about the chemistry of the source of that magma in the deep interior. And another one is the synoliths. So it's also associated with magmatism, but the synoliths are foreign particles. When the magma is ascending, so this break down some wall rock from the interior, and it's come up with these foreign rocks. So when we get the rock, we can analyze, and that are the good samples for the maybe mantle or the upper mantle. And sometimes it comes with diamonds. Sometimes it's believed, study shows that the diamonds are coming from the core mantle boundary related to plume activity, and with these diamonds include some inclusions of the lower mantle minerals. So since the diamond is too hard, and it can withstand too high pressures and temperature, the inclusion is during the ascent is very safe. So what you are getting is the direct sample of the lower mantle. So this also shows that, as you know, the temperature and the pressure. This is one of the intrinsic property of planetary bodies, especially the Earth, is the temperature and the pressure is increasing with the depth. And these are the phase diagram, not complete phase diagram up to the lower mantle. As you can see, different layers constitutes different minerals with different structure. And this maybe you studied in textbook as a phase transitions. And this is about the phase diagram of iron under extremely high pressures and temperature. So this kind of we have this kind of phase diagrams also to explain the physical structure of the planet. Then so this also a phase diagram for the pyrolytic mantle, pyrolytic bulk composition as a function of pressure and temperature. So here also shows different minerals with different phase transitions. So the question is how we know these kind of phase diagrams, how a particular compositions change. It's converted into new mineral phases, or a mineral phase is transferred to another form. How we can study? So the answer is there is a particular field which deals with this kind of study is called mineral physics. So the mineral physics, two kind of approaches there. One is the experimental mineral physics and another is the computational mineral physics. So my 2 years, I worked on the experimental mineral physics approach. The approach is just a brief diagram that there is a sample of which is relevant to the planetary interior. Then we apply the pressure and temperature. Then we see what's the results. First we see what's the crystal structure. Then associated with this crystal structure, what's the physical properties such as the electrical conductivity and the thermal conductivity, and also we measure some elastic properties like the bulk modulus, rigidity modulus, to explain the seismological observations. Then, so the key idea of mineral physics is we have a pressure and temperature and static composition. Then we want to identify what the structure. So there is a correspondence always between pressure, temperature, static composition, and the physical property. So the mineral physicists do we want to find this kind of correspondence. So there are several type of compression techniques exist to generate high pressures and temperature. So it's classified into two. One is the dynamic compression and another is the static compression. So in the dynamic compression and the static compression, the classification is truly based on one is when we doing the experiment, whether the sample is experiencing homogeneous or hydrostatic pressure or not. So if there is no, it's too far from the hydrostatic condition the sample is experiencing, then we call it dynamic compression. And if it is too, very close to hydrostatic condition, then we call static compression. So one of the techniques in the dynamic, the most commonly used the technique in dynamic compression is we use laser to produce shock waves, and these shock waves exert pressure on the sample. So another is the, as I mentioned previously, static compression, and this is, more hydrostatic. The sample is experiencing more hydrostatic conditions. And also there is another techniques called diamond anvil cells. So this can reach extremely high pressures and temperatures, but there is some limitation is there. In the diamond anvil cells, you can use very small sample size, which is even micron size. And also within the diamond anvil cell, the sample is experiencing, there is a pressure gradient within the sample, and also there is a temperature gradient. So, so this is just a schematic of diamond anvil, and so my expertise is in this kind of, there's a particular kind of compression technique exists, which is called Kawai type multi-anvil press, which is developed by N. Kawai. He's a Japanese person. So the advantage of using this compared to other is we have the sample size which is millimeter to centimeters, sized in dimensions, and also we have more hydrostatic. I will not say that it's a truly hydrostatic, but there is a, it's more close to a hydrostatic condition, and also within the sample there is the, we can control the temperature gradient. So the temperature gradient within the sample is negligible. So so in most of the chemical and physical property analysis, we need large sample size. So this is the advantage, but there is a disadvantage of this this technique is that the maximum pressure and temperature achievable by this method is very limited. So Kawai type multi-anvil press have several components. That is, one is, so technically, I will use a technical term that is cell assembly. A cell assembly is defined as a set of components. The components are listed as heater, electrode, thermal insulator, pressure medium, and these are systematically arranged. And also we use different kind of material, and also the dimension of the each component we can vary. So it's kind of, the research is mainly iteration. So we try several materials, several dimensions, and see how we can generate maximum, pressure and temperature in a efficient way. So, so these are some, in the name mentioned, multi-anvil. The anvil is this one, the, these cubes. These are tungsten carbide. I use a particular kind of tungsten carbide called the TF05. It's a one kind of grade with certain properties, hardness and such things. And there is you see these truncations. So these are very critical for high pressure generation. That tapering is called the truncation. And the cell parts are, we always use a pressure medium as a octahedra. Usually it's a magnesium oxide with the chromium doping. So so this is generally used in all high pressure experiments in the multi-anvil is the chromium doped MgO. And usually what we do is we make a hole, a cylindrical hole, and all the assembly, assembly means the heater, thermal insulator, electrode should set in that particular hole with including the sample inside the cell. So, and to measure the temperature, we use thermocouple. So usually I use tungsten rhenium thermocouple. So as you can see, there is a junction at the center of the sample, and also you can see a black color. So that's a heater, and outside that there is a white portion. Is a zirconium oxide thermal insulator. So these are the just photos. These are the other photos. Finally, it's in the form of like this, and that is in the left bottom. So you can see the recovered sample. So these are the instruments at my institute. It's a very commonly used instrument in high pressure. So these are some pressure temperature conditions that can be achieved by the different kind of techniques. KMA means the Kawai type multi-anvil. As you can see, recently 110 GPA is achieved from our lab by Yamasaki. So, but it's relatively at low temperature, as you can see, around 2000 degrees C. But you see, the high temperature generation is restricted to around 4000 Kelvin. So my study at the IPM is about to develop the technology further to simultaneously achieving the pressure and temperature together. So I done several attempts. One is the room temperature pressure calibration for 8.3 cell and 5.1.5 cell. 8.3 means, as I show you before, that there is a truncation. So 3 means you saw before a triangle. So it's a equilateral triangle. So one side is 3 millimeter, and 8 means the edge length of the octahedra. That is the pressure medium. So A3 means this is the notation. So, and also I done pressure calibration at 2000 Kelvin and 2000 Kelvin pressure calibration, and also I done heating efficiency test for a newly discovered heater called boron doped diamond, which is a semiconductor heater for the 5.1.5 cell. Then these are the cell assembly I made. So as you can see, it's look like this. The pressure medium, and I used for the room temperature pressure calibration. I used two pressure calibrants, gallium phosphate and zinc sulfide. And the idea behind is we can control the force that is applied by the press, and we know some materials which have no transition points. For example, gallium phosphate around 15 GPa at room temperature, it transforms to there is a transition between semiconductor to metal. So I measure the resistance. So once the resistance drops, then it's confirmed that the phase transition happens. So the force is, then we make a plot between force in meganewton versus pressure. Yes. So pressure versus force. So that's the calibration curve in high pressure. So yeah. So these are the calibrations I mean, not everything I made. These are some which includes other also. So these diamond and this one is I modeled a so I made a cell assembly and I calibrated this pressure. And as you can see, the diamonds, it's almost reached more than 30 GPa, which is corresponding to the top of the lower mantle. And also, see how it's done is given in the table. And also I done a
Just
calibration for
please conclude.
yeah, 2000 degrees C. So I use the pressure calibrant as pyroglass, then uh, so this is the pressure calibration curve I obtained. So this also, at high temperature also I reached 30 GPa. So this is the boron-doped diamond test. So this is the cell assembly developed by me. And this is the heating results. And so this is the calibration curve. So that newly developed cell is almost reached from the power temperature relationship. We know that it's almost reached the 5000 Kelvin. So the key conclusion is that I expanded the temperature generation from 4000 to 100 Kelvin is I increased, so which is corresponding to around the lower portion of the outer core. And pressure, with my newly modeled cell assembly, I can reach 30 to 40 gigapascal pressure and 5000 degrees C. And there are several applications. We can determine the phase relations, peridotite or pyrolite melting temperatures at high pressures, and this cell assembly I newly developed is best for study the viscosity of melt using synchrotron X-ray facility, because boron-doped diamond is transparent to many of the electromagnetic radiations, especially the X-rays. So, thank you.
the chairs can actually just put me some signal at 18 minutes so that I will control it. So, so that I will wind up it. So that's good. So very good morning to all. Yes, it's good morning. Then distinguished delegates from international and national arena, the organizers, very vibrant organizers of this seminar. I heard a lot about this gem. Last time my friend and colleague, active researcher Lindo, called me at that time, I don't know, due to some thing I could not come. So this time also they invited. Then friends, my colleague, my friend Professor Maurya is there. Jyoti was there, her face is missing. Jyoti Srivastava. So very good, I think then students, my beloved students. So the introduction, they talked about sustainable development. Yes, I worked on sustainable development in environmental geology, but I also worked on quaternary geology, especially late quaternary sediments of Kerala coast. So you should address in that way so that they will get a feedback. Instead, you just divert. So, yeah, next slide, please. So my previous slide, you go. So my talk is on decoding the late quaternary evolution of Kerala coast using some multi-proxy analysis. For the past 20-25 years, I worked along with the different researchers of national level and also international level to some extent. And I'm telling only the story. So I won't use all proxies here because this 20 years of research and decoding something, the evolution episode, and putting all the supporting evidences will be very difficult. Instead, you can actually go for Patmalaldi or something like Google or my Google Scholar. Then you will get the papers list. So you can, if you are getting it, you take it and read. Otherwise, you can just contact me. I will send the copies to you. So in some of the, so I won't be sticking more on the supporting evidences, and I'm talking considering the youngsters, young researchers. What is the story behind it, so that actually in future you can work on it and strengthen it. Sometimes I have created errors in my research. Research is not 100%. So there will be errors in different things, and even in each paper there will be mistakes, and in the future community, based on the advancements of the instruments and all other things, now you will correct it. So I am just telling you the update, what I have done it. So you can develop it in future. So decoding the late quaternary evolution of Kerala coast. Next slide. Right, about my presentation, I will talk about some geo-environmental setting. Then I will talk about the coast perpendicular wetlands or lagoons or backwater bodies. Then the coast parallel systems. Then little bit about the Kuttanad cold wetland. Somebody was talking about the Pampa river is confluencing, joining in the Kuttanad. A little bit about the Kuttanad if time permits. Then some highlights of the study. Sometimes I will skip on that. So this is the coast perpendicular estuarine systems. You can see the Ashtamudi estuary. Mudi means arms. Here 8 arms are there. 1, 2, 3, 4, 5, 6. Just like 8 arms are there. So and another interesting thing is that if you are looking into this region, some of the water bodies are there. Satellite water bodies. So we have the main Ashtamudi water body. Then the upstream end or the upper estuarine region, you have these satellite water bodies. Likewise, a miniature form of Ashtamudi is here. What is the sound in that? It's some problem. So here you have the Paravur estuary, then some few satellite water bodies there actually. So why these are all seen in the uplifted cliff coasts of, what is it actually? My voice is high? Now okay, yeah, you can adjust it. So these are all, I will use it. I can remove it and I will talk. And that will be free. You can stop. My voice is very good. You can understand. So let's give it. Now it's okay. You can hear. Last person you can hear. Yeah. So I will talk about the evolutionary history of these two. Next slide. Yeah. So you all know that we are in the monsoon domain. So this red dotted line is the monsoon domain, and it's spreading in Bangladesh, Pakistan, part of China, part of Africa, and part of just like Sri Lanka, and India is at the center of the monsoon, the core region. So that's actually you may be knowing that the monsoon is tightly connected with the global forcing mechanisms like El Nino, La Nino, Indian Ocean dipole, and other things. So any change in the global forcing will have an effect on the monsoon demand, and this will be reflected more in the more region and Indian economy, greenery, life, everything is controlled by the monsoon. So monsoon, any change in the global forcing will have an effect on this monsoon, very well reflected, will be reflected in future or the present in age. And if you are looking into Kerala, this is in the southwestern part of India, which is the gateway of Indian monsoon. Monsoon cloud from Arabian Sea is entering in Kerala, and we have the western Ghats along Kerala, which is towering mountain system, which is close to the coast. The maximum average width will be 40 kilometers, 40 kilometers. Minimum will be few kilometers, maximum 120 kilometers. The center, Ernakulam, the Maurya district, Ernakulam, where the western Ghat and Kerala coast will be the maximum nearly 120 kilometers. So we have a close mountain system down the coast, and the monsoon is entering, and once this updraft, the clouds will be there and precipitation. So I mentioned that the monsoon domain, India is the center, and Kerala is the very critical area. So any change will be first affected, or Kerala will be the first victim of monsoon dynamics, monsoon changes, or landslide front because of the particular geography set, western Ghats. And the beauty of this region is, another beauty of geology is that this western Ghats, weathering and erosion of materials, will be best preserved in the coastal sedimentary archives. It will be preserved. So if you are looking, if you are taking the course and analyzing it, you will be able to decode the past climatic conditions. And in India, it is first place where the monsoon is entering, where the archives preservation is actually possible. Somehow, I could work on that particular area and try to understand the things and tell the story to you. You can tell after eating. So this is the west, the towering western Ghats. Maximum height will be 2,600 meter plus something will be the maximum. And it's a towering mountain system which is accumulating the monsoon clouds and giving precipitation. This region and sediment dynamics, everything is controlled by this system. Yeah, and we heard a lot about granulite and another thing. This is actually the southern granulite terrain. And in southern granulite terrain, here you can see the Irinjalakuda shear. So many shear zones are. This is a Palakkad Kaveri shear. The Irinjalakuda shear zone, south of the Irinjalakuda shear zone, the rocks are from Kerala to which contain carbons and nice. So my would be sillimanite and nickel. And in the Madurai block, it's essentially composed of charcoal-based nice so there is a diversity in geology. And I am working on the fossil next time. I am working on Thrissur. And this region is the actually sediments from the Kerala Kondarite, where it is contributed, and the Madurai block itself. This is a 12 block and this is Madurai. Both things are actually contributing sediments to the. You asked that question. Yeah. Previous slide. Previous slide. No, that's yeah. Please. No. Come to this. Yeah, forward. Yeah. Again, the current system, if you are looking at the current system, this I have put from the recently published paper. And we have the western Indian coastal current moving towards the sediments are actually taking and moving towards the taking to the northern side. But in the monsoon season, some reversal. A few months, sediment, the current system will be reversed. Sediment will be moving in the other side. But the next she calculated how much sediment is actually moving towards the northern side, northerly drift, and the southerly drift. The net drift is towards the northern side. And these minus values are negative. But actually it's only little bit. But the net drift will be towards the northern side. Means that the sediments are moving from this side to that side. No. Covering these two blocks. Next slide. Yeah. So through my 20 years of work, along with my gurus, Professor Lakshman, Dr. Kemna, and also colleagues from National Treasure, we worked on this with the gateway figures about like the sedimentary archives. And my guru has contributed the Cenozoic stratigraphy. The Cenozoic stratigraphy means no, it is nothing but the landward extension of Kerala Konkan Basin. Maximum thickness of sediments of about 700 meters near Alakuda is a backwater system area. Tourist center, boating and other things possible, where the maximum thickness of sediments are there. And the sediment, in 1980, he came with this kind of benchmark information, or to a benchmark for the. Then Dr. K.M. Nair, he was the director of INSES. He worked with me for about 20 years. And next slide, please. Yeah, this is the entire Cenozoic sedimentary sequence. There is a tertiary neogene sediments are there. Above that quaternary means late quaternary. And I worked on the late quaternary, and we came with through hundreds of boreholes along the coast. We came with this information. This particular letter, 2014. About 100 kilometers through hundreds of boreholes, expanded this 100-meter level to this track. You can also test and take some borehole and the like. So the maximum thickness, again, even the late quaternary, we won't get the full thickness of quaternary, only late quaternary, maximum thickness coinciding with the central phase. So next slide. Yeah, yeah. I'll be talking, this is the post-perpendicular system, entrance on the geology. I told you I will be discussing on two aspects. One is the post-perpendicular system. This is the Ashtamadi basin, the channel fortification, basin fortification. I could not go up to the bottom, only up to 14 meters. I drilled, analyzed it. And here in Paravur basin also, I think 30 meters or so I drilled. Next slide. In plan, it will be like this. So this is the Ashtamadi system. This is the Paravur system. I think it's clear. Yeah. So this is the plan I have shown. So I studied the sedimentary sequence of this area. This color is actually alluvial deposits. I think Holocene sediments. Took many boreholes from this. So I want to see, how this is formed. So we have the main master body of Ashtamudi with 8 arms, then satellite. How it is formed? That was the first on. And along with my students, I worked. I took boreholes, data, analyzed it. Next. Yeah, different boreholes with all sorts of materials, subfossil woods, palynology, geochemistry, textile analysis, geochemical analysis, whatever you are presenting in modern or ancient, I have done it. So gone through it. And next, even isotopes, stable isotopes. Previous slide, yeah, you can see the buried logs. Some of the logs are in situ, in carbonate square. Some of them are uprooted, lie in different fashions. Took the sections, analyzed with the help of GSI. So Dr. Kumar and sir and scientists of GSI, they worked on what type of whether evergreen vegetation or semi-evergreen, all things recorded. And I'm not going through that aspect. Next. Yeah, I also analyze the heavy metal. That is one of the best tools. I'll tell the beauty of it. Next. So took many cross sections. These are the satellite water bodies, 2 satellite water bodies. or satellite water bodies found in the upstream side of the Ashtamani system, across and along river to boundary, everything analyzed, mineralogy also analyzed. Next. Yeah, then how it is formed. Some 10 years back, I was sitting around with my colleague, Irinjalakuda. He was a GSS, BAS remote sensing specialist. He was working on the reservoir planning. I told him, can you just remove this, this yellow color, that part, that little bit. I want to see the original configuration of the site. Can you, by using some technique, can you remove this part, this part? Is the holocene sediments, entire thing is holocene sediments, which is the entrance device. This part is section. Next slide. Then we tried, this is yellow color. I told him just remove. Yeah, remove. So I got the mega lagoon, which was not eight mudis in Sanskrit. 8 arms, Ashtamudi. Ashtam means 8 in Sanskrit. Sanskrit is an older language. It's 8. It was not 8. Now I got 12 arms. This is Dwadashamudi, 8 to 12 arms. So I got 12 arms. The mega pre-Holocene basin was 12 arms. Next. Yeah. Half of this basin are filled with monsoonal sediments from the hinterland, western Ghats and other thing in early Holocene. Climatic optimum is climatic high. The rainfall was 3 times higher than the present. That much sediments, half of the basin are filled. And now turn some of the arms cut off from the main water body to discrete water bodies like Shasta Water Lake, Chendupola, Chittimalachura, satellite water bodies, and the rest remain. The beauty is only 200 meters is actually here. If that 200 meter also deposited, we would have been received a wetland system of 5 times more than that of Shasta Water Lake. Shasta Water is the largest freshwater system in Kerala, but we would have been received another one of 3 or 5 times higher than Shasta Water Lake if 200 meters of sediment might have. But before that, climate change and another thing put on, even we can construct a bond and keep it for hundreds of years, this will transform into freshwater. Also, so this actually published in many papers. Different papers published, you can read it. So next, yeah, once again you can see it. Yeah, how the things are coming and deposited. Now, yeah, how it cut off into the lakes, how it's sewer. Next, yeah, this is the depth of the basin at present. So here the maximum depth of the Shastakota Lake, in the freshwater lake, the depth is 30 or 30.5 meters. Here also there are many 38, 6 meters deep depressions. So in the Holocene, sea level rise has brought a lot of sediments from the coastal area. The rainfall and terrestrial sediments came into the unfilled zones in red, even now. If I'm putting in Dalrymple model, so we have the barrier islands on the coastline, and we have the Bayhead Delta. This kind of sediments, they are calling, Dalrymple is telling in this benchmark paper, they are telling us Bayhead Delta. In West Coast, usually we won't get the delta because we have high wave energy, we won't get that. But we will get micro deltas which contain a lot of archives, and Jyoti and team can work on it and decode it. And I won't get that kind of, I didn't get the opportunity to do that. But these are all the first archives you can do for climatic and heating. So this is how we decode the things. Keep it in mind for any researchers, you can do. Sometimes my concept will be wrong, you can do it and you can clarify me. So what you told is wrong, you come and do it. I will also do work and I will discuss and debate and find tune. Next. 42 minutes left. Next. So previous slide. We constructed the sea level positions and other things. Not going into that. Next, coming to post panels. Game graph. How this is this part. The beauty is little bit lack of geology. I'm not a specialist in that, but I said that Still, I heard that you talked about him. But this information is required, otherwise you cannot track it. So this side, the Kerala Condolite belt is there, which can bring, which can contribute sillimanite, heavy mineral, light heavy mineral sillimanite. Then how it is migrated? Yeah, so I'll be focusing on this. This part is actually membrane position, that box. Next. Boreholes, different countries, fully selected boreholes. Yeah, very interesting thing. I think I'll have to take one more minute or two. So very interesting thing is that this is the contact between this, almost this is the lake bay. This is the contact between the Trivandrum block and the Madurai. So in Trivandrum block we have the condylite, sillimanite, this one, this color, this white color, sillimanite, light heavy. It can be contributed only from the Trivandrum block, this part. But I've got indications, attract the occurrence of this sillimanite up to some 80-100 kilometers from this mineral. It cannot come because the hinterland is composed of this kind of fireballs, pyramsens and mandibles. One or just like that. So we cannot expect it. So in the Paleo time, the early Holocene time, if I'm taking the boreholes, it reaches up to a regular, very well. In the subsurface, we have sillimanite. In the hinterland, no sillimanite. How it is not? Then in the present beach also, up to Marari from 80 kilometers, is free. How this storm structure? See, another interesting thing is that in the southern and near Chavara, Nendagara, Ashtamudi river mouth area, we have the world's largest beach plains. Ilmenite monazite, the talking about monazite. Ilmenite monazite, large part. More than 96% in the region. Of course, the Indian rare earth and Kerala metal and minerals, they are extracted. Monazite is brand new atomic beach. We want to Spanish because that's Spanish. And if you're seeing you will get a morphological feature, a ridge runner system up to this. And here you have silica sand deposit. Earlier you classify the organic glass industry. More than 99.6% is silica. Sands are. Here, thing is heavy. Is it density basis of thing along the longshore drift? Yes. My indicator minerals are reaching up to. Even in the silica sand, I will get a very fine grade sillimanite. Larger coarse grains with the small grains of sillimanite. Hydraulic, if you are studying this Ruby's hydraulic equivalence, the larger grains of lighter minerals will be equivalent to smaller grains of heavier minerals. And this combination you will get up to this Chertala. Means that longshore drift was very active even during next slide. During Holocene. This is from Ajit. So the rivers draining this region will have the sillimanite, light and other things, whereas the rivers draining this Madurai block will have the hypersteal formula and other type of mining. So this is also rivers, but this has reached to up to that because of the longshore current which is operating in the left part of the field. Yeah, Venus computation, even now the longshore is operating. I'm sorry again, I try. Oh, I want to eliminate this quaternary left quadrant. I want to see, I want to see the original base. How? Again, I depend on GA specialist. They have the pre-Holocene banking and payment. So sea level was at that time. We have many fossil content in the boreholes and other things. If you are drilling, the rivers are directly debouching. Many evidence. Going into the just you can read my paper or some other papers. Next. Yeah. Lots of in the form of spits, and spit mapped together barriers, and the backwater body is slightly separated. Everard lake water is in the origin, in the mapping, in the middle Holocene. Next. Yeah. Some of the same planetary. So we have to approach in different ways to decode the evolution. When I am talking about this Rembrandt and Activity, almost 100, 150, 200 kilometers are covered here at coastal side. We have to approach in two processes. Next. Yeah. Then I worked about on this particular idea. This is Kottala Old Wetland, where one of the earlier speakers student explained. So my problem is that in this area, three rivers are debouching. One is Achankovil, then Manimala, then this Pamba river debouching. And it can go, actually, this is a confluence type of area, only 10 kilometers is in between. You can travel 10 kilometers. Instead, it took some 20 kilometers here on two spells. It went and joined. Why? It's not required, actually, directly, because the barrier built up process plus technology. I don't know. I think nobody can. You have to work on it. I will tell you. So a lot of gap areas are there. So why? What is the reason? This is covering some 20 kilometers and debouching into the southern end of the Vermont Lake. There is no need. It can go up to the Kottapalli region and debouch. The channel is also there. It can be active. Because of this barrier and split development, and another interesting thing is that here at the end of this the southern arm of the Rembrandt Lake, we have this yellow colored region that is nothing but the subfossil cells of Geologists. It's a bivalve. Age is 4,000 to 3,000. If you are collecting the bivalve from here and dating it, you will get only 4,000 to, generally you will get 4,000 to 3,000. Why it is sticking to 3,000? Beauty of Geologists is that it will thrive only on the freshwater in the fresh. It is only in the upper echelon, where the river is bounced. So 3,000 to 5,000 years, 3,000 to 4,000 years, a freshwater end of an estuary formed there, which actually proliferated ambience and habitat for proliferation of Geologists, and we are getting deposit, economically viable deposits of subfossil. Means that at that time only these rivers diverted and reached mid-morphosis levels. Anyway, I tried, and in my recent book, next slide, on Monogen Climate Change and Environment, is an edited volume containing many papers of me and four authors and another thing. I think it's 21 K. It's a bestseller. So in that it is there. You can read what is the in the pre-Holocene, how the line was, that Irinjalakuda was there, in the middle Holocene, late Holocene, and what is the level, see the positions of the shrinking of the neck basin through Holocene, everything was done and explained. And evolutionary stage is also made, because that is from the southern end of the more focused study. I'm not taking much time because I'll be jumping into the other speakers' time. Because this is a nutshell. I have not supported with the evidences and another thing. You can read the papers, and if some doubt will be interested, because in a gathering, only one fellow will be inspired. Sometimes nobody will be inspired. That's the beauty of research. Maybe one good paper will be reading 10 hours. Sometimes 20 hours. Maybe senior researchers know. So those who are interested, you can approach me or send me or we can connect. So I in the morning I got friend from OIGC, because I worked under Dr. K.M. Nair. He always tells, Padmanan, I worked on 3,000 meters course analyzed it. You are talking about 30 meter or 20 meter. What is it? Nothing. So under this OIGC scientist I worked, so that I could work out on the basin configuration and other things. Next. I put their photos and other things, my gurus, with a few acknowledgements earlier. These are all the points to take. There's no new text. These are all the persons to whom I worked. My students, colleagues, Dr. K.P. Kumar, Dr. K. Nair, Jim Janandan from Israel, now Chen Ruka, many students. Arul is not there. No. So it is not my contribution, and it is there. I only made the presentation. I know that there are different drawbacks because supporting evidence is, but we read it. Otherwise, when I started, no, nothing was there in the quaternary of Kerala, very important region where the monsoon is entering. So any change in the global climate system will have a reflection on the Kerala coast. We are facing flood in 21, 18, 19, 20, 21. So global climate change is that then you are talking about landslides and flood and another thing. No, you can expect because this is the entrance of the gateway of Indian summer monsoon. Where we have the good sedimentary arteries and people have to work on it directly for it. And this red are actually our own work, but now Linjoy is working, BSIP, Jyoti, I think will give more attention to this, is it not now? Otherwise we cannot fully. So BSIP, Kerala University, Linjo and group is working on many papers is coming, and that's why I am coming and talking about this kind of things to you people. You enrich, you just point out the errors from me. It's not a challenge, but yeah, you can discuss it. Thank you very much. I am all obliged.
I can officially say good afternoon. Esteemed colleagues, and most importantly, students, it's an honour to be here, and I would like to especially thank Lindsay for not just inviting me here, but making it possible, because there were some difficulties with the visa to be here. So thank you so much for inviting me. Where do you think I am from? Wrong. Where are you from? Wrong. We are all Africans. We are all Africans. And that is an important thing to remember. It's important to remember for several reasons. And one of the reasons I asked where you're from, and I replied, we're all Africans, is that I want to take you to Africa. And I want to do this because this is, in southern Africa, a part of the world where I've been working for 44 years now, but also because it is the cradle of humankind. And there are many questions about human survival and today and into the future that we're all concerned about. But we can also learn a lot about how our ancestors and how the evolution of Homo sapiens has coped with different environments and environmental change. So I want to take a multidisciplinary approach. And I like your talk, sir, because first of all, you talked about multi-proxies, but you also said that we have to work with others. We can't do it alone. So I have, what I want to present to you here is a piece of work that addresses a problem about early human behavior, and a problem that we could only solve by employing a multidisciplinary approach. I'm a geomorphologist. I work in a geography department, not an earth science department. Many of my colleagues are social scientists as well as natural scientists. But in this piece of research, we have combined geomorphology, geochronology, archaeology, and geochemistry to answer a question. And without employing multiple scientific tools, we're not often able to answer many of the pressing questions that science is asking. So I want to look at how we've integrated these different techniques, these different disciplines, to address what may not seem a very important question to you, but it's a very important question in our human journey. And that is, how have we been able to survive in different environmental conditions? How have we been able to cope with the extremes of climate? And these are very prescient questions given what is happening to our atmospheric and Earth system today. There we go. So I want to take you to, we just check, is that my, that's my set. I want to take you to southern Africa. And I want you to notice a couple of things on this slide. First, the big flat interior, and secondly, the uplifted coastal zone, which has been, the next slide, which has been an, I don't think this is working. Yeah, okay. I want to take you to the interior Kalahari Basin. So the interior of southern Africa is a big sediment-filled basin that has an area of about 2.5 million square kilometers today. And it's mainly dryland. It's mainly arid to semi-arid. It's driest in the southwest, and it's more semi-arid in the heart of the interior. It's a basin that formed with the uplift of the periphery of Africa with the division of Gondwanaland, and since that time it has progressively filled up with sediments. So it potentially contains a very significant sedimentary archive. Next slide. It's a very diverse landscape. I've spent a large part of my career studying the dunes that are a very significant part of the Kalahari. But it's also a diverse landscape, next slide, and it's a landscape that contains river valleys, a landscape that contains wetlands, including the Okavango Delta, but also paleo lakes. And one in particular that is my focus is the Makadi-Kadi Basin. Now, I looked up on Google last night to find out what the biggest lake in India is. And I was very, very disappointed, because you do not have big lakes in India. The biggest lake in India, according to Google, is the lagoon we have just been hearing about, 2,000 square kilometers. The biggest pure freshwater lake is only 1,000 square kilometers. Next slide, please. I want to take you to a landscape where lakes are huge or have been huge in the past. So the Kalahari, as that map shows, which I won't talk about in detail, is a very complex, has a very complex geomorphology, but a geomorphology where the surface landforms preserve a history of fluctuating levels of humidity. Paleo lakes, evidence of wetter conditions in the past, dune systems, far more extensive and active than those that are mobile today in the wind, indicative of drier conditions in the past. And I want to take you to the Makadi-Kadi Basin. And I want to look at what appears initially to be a very unpromising place to look for evidence of early human life. But what we have done is identify that, contrary to popular scientific archaeological theory, the dryland interior of southern Africa has been a key place where many aspects of human evolution and innovation have played out. Traditional theory in archaeology says that during the Middle Stone Age includes the period when we left Africa about 100,000 years ago, but during the Middle Stone Age, conventional wisdom has it that the interior of southern Africa dried out and any early human populations that were there dispersed to wetter upland areas and to the coast. But our field evidence suggests otherwise. And by employing a range of different techniques and joining up people from a range of different scientific disciplines, it's possible for us to first identify material that has shown that humans, far from being absent during dry periods, were very significantly present, but also to answer the critical question, how did they survive and why were they there? Next one. So what I want to do in this talk is give you an indication of what we've been discovering through what I think is the first systematic analysis of the Middle Stone Age geoarchaeology of the Kalahari Basin. So let's have a look at, let's go back to this beautiful image of Africa. Traditionally, archaeologists, and there is one in the top there, traditionally archaeological work has tended to focus on the rock shelters found around the coast and in the upland areas. And these are sites which preserve very often very significant Middle Stone Age records spanning the last from 250,000 years ago up to about 25,000 years ago when we became truly modern, but embracing a period of human history where we learnt to innovate, where we learnt not just to survive, where we learnt to use materials out of the landscape in novel and new ways. And theory has it that the best places to innovate as a species were around the coast in particular, because around the coast there's a constant supply of nutritious food. And dietary archaeologists often argue, and human evolutionists argue, that it's the nutritional value of marine food that actually led to an expansion in the capacity of brain capacity. So the assumption is it was only because people were at the coast that we evolved in a way that actually allowed us to think and to cognate and to do the many different things that we've evolved into doing. Next slide, please. And when you look at maps of the Middle Stone Age archaeology of Southern Africa, you'll find that there are just one or two places represented in the interior dryland region. Next one, please. It's the coast, particularly caves such as this one, Blombos Cave, which has a fantastic Middle Stone Age record of human behavioral change. The first evidence of the making of beads. The first evidence of art, etchings on stones. The first evidence of the use of pigment. All found around the coast. Next slide. When you look at maps of key archaeological sites in southern Africa, you see maps such as this one over here. Rather like my cartoon earlier, all the key sites are around the coast or in the uplands. The middle is an empty place. And in 2019, a very significant paper based on modern DNA studies was published in the journal Nature. And this is a graphic from that paper. And it suggested not only that East Africa was not where our origins were, but actually it suggested that the real key ancestral DNA-based evidence for where we all came from was a wetland in the middle of southern Africa, the Makgadikgadi-Okavango wetland, which, according to this paper, dried up 130,000 years ago, causing dispersal to coastal areas and into East Africa, and then later on, about 100,000 years ago, out of Africa. That paper is very controversial, and the DNA work within it has been very much criticized and found to be at fault. But it's an influential paper, and I still go to conferences where it's put forward to say that the Kalahari, particularly the Makgadikgadi-Okavango basin, is where modern Homo sapiens dispersed from about 30,000 years ago. Next slide. Next slide, please. But that feeds very much on the idea that the middle is empty. And the archaeological record, as generally presented, would support that idea if this record is correct. But if we go back in time, if we look at old literature, and sir, you said earlier that people may find you to be wrong. I view it as very differently. I view science as a constant process of hypothesis testing. And as new techniques become available to you into the future, old ideas get revised. But also, old ideas sometimes get forgotten. And we found, whilst we were working in Botswana, that back in the 1950s, the first geologists under the old colonial system to be based in Bechuanaland, which was Botswana, the name of Botswana before independence, he had traversed the Kalahari landscape in a painstaking way, finding stone artifacts almost everywhere, evidence of early human existence in the desert. But that work had become forgotten. So I think as you look into the future and do new research, never forget the old research. It may get refined, but often there are little gems there that get missed out because so much is published today, people forget what was said before. Next slide, please. And in fact, we then, this is the research team, we went and looked at what we sometimes call the grey literature, not the papers published in the big journals, but the little pieces of research that's in small regional journals or in reports. And we found actually around Makgadikgadi and the Okavango, there are many sites shown by the numbers here that represent the Middle Stone Age. Next slide, please. And then since in the last 2 decades, including our work, which is the dots in green, our work as part of the project we've been carrying out in the last 10 years, found hundreds of sites, surface Middle Stone Age sites through the Kalahari. Next slide, please. And what's interesting is that, bearing in mind the Makgadikgadi Basin, that saltland, that dry paleolake, very inhospitable today, many of those sites are in the Makgadikgadi Basin. And many of those sites are on the floor of the dried out lake. So how is it, if we are meant to have left 130,000 years ago, that there can be so much lithic material, and it's not early Stone Age, on the floor of this dried lake? Next slide, please. And furthermore, this lake has a very complicated history. If your biggest lake is 2,000 square kilometers, the biggest lake in Africa today is 70,000 square kilometers, Lake Victoria. Makgadikgadi, this basin, has a history of fluctuating lake levels through the Lake Quaternary. A colleague of mine, a former student of mine, did her PhD reconstructing, through luminescence dating of shoreline deposits, the hydrological history of this lake basin over the last 150,000 years. And we have found, as the blue bars show here, that this lake has gone up and down. It didn't dry out 130,000 years ago. It's gone up and down in response to global climate changes many times, with 7 or 8 major lake high stands over the last 140,000 years. The most recent one about 8,000 years ago. And that lake in the middle of the Kalahari Desert, bearing in mind that Africa's biggest lake today is 70,000 square kilometers, and India's biggest lake today is 2,000 square kilometers, that lake was up to 90,000 square kilometers. Africa is a landscape of big lakes today, but also evidence of even bigger lakes in the past, often in what are today's desert areas. Next slide. Now, as well as working on the shorelines, we've been drilling that lake, because if you remember, this is a basin that has filled up with sediments since the division of Gondwanaland. We took a big drill rig out about 10 years ago. It sunk into the sediments. We only got 6 meters of core out, and those 6 meters of core actually go back over 30,000 years. We've now, on a new project, drilled 250 meters of sediment, and they go back to they hit the basement at the bottom, which is about 4 million years old. So there's a big depository of sediments there that are also, which I'm not going to talk about, are revealing a complex history of a big lake going up and down. Next slide, please. But also, whilst we were there on many field trips doing field research, we could not help but find that the landscape of that lake basin, which today is dry, is full of archaeology. Most of it is, or much of it, or most of it is Middle Stone Age lithics, but there's also pottery, there's also later Stone Age, finer tools, and also pottery as well. And what we have done over, as well as mapping the sites, what we did over 2 long field seasons is excavate 6 surface archaeological sites off the dry lake floor. Next slide, please. And we found incredible evidence of human innovation in the desert. Each of our sites was a single-use site. People have been through the landscape, napping and making tools out of black material called silkrete, which is quite prevalent in this landscape. There are many silkrete outcrops. Making tools, beautiful, perfect tools, and leaving behind waste flakes that actually the archaeologist on the problem could this is one of our archaeological excavations. Each dot is a tiny bit of lithic. One of our archaeologists was an expert in refitting material. She could rebuild the rock that the tools had come from. And normally the tool was missing out of the middle. It had been made in this dry desert landscape. The waste had been rather like the plastic litter that we leave today. Our Middle Stone Age ancestors left their rock litter on the landscape and moved on to another location. Hunting, probably hunting. There are hundreds and hundreds of sites like this over the floor of Makgadikgadi, and we excavated 6. So the one key question is, if this lake has gone up and down since, so this is Middle Stone Age, if this lake has gone up and down, including big high lakes in the Holocene, how has this remained basically undisturbed? How is it possible to put it back together again if since this was allegedly made, the lake has been a big deep lake, maybe 20 meters deep, with currents and so on occurring in it? Next slide, please. So we have a question. Why is it there when people were not meant to be there, according to archaeological theory? We have another question. What were they doing there? Well, they were probably hunting. Another question, why were they bothering to be there if it was dry when they were there? Because the lake must have been dry, but these tools haven't been washed in. They were made. These are sites where napping took place and material was made, and the remains of what they did are undisturbed. So let's have a look at a couple of our archaeological sites to just try and answer the question. So this is a drone shot of part of the floor of Makgadikgadi. The green areas are small sand dunes blown up by the wind from the lake floor sediments, which are sandy silt. Next slide, please. These are 2 of the sites that we excavated, and you can perhaps see some pits and trenches there that after the archaeological work was carried out, those of us who deal with the sediments dug sedimentary pits to sample, next slide please, and next slide again, to sample the sedimentary context of the archaeology. And what I hope you can see here is that this is a pit dug into one of the sand dunes from that last slide. And in that pit, you can probably see darker sediments with a stone tool, with a lithic sticking out, with more darker sediment above it, and then above that blue line is the dune sand. And these are, we've taken samples for luminescence dating, both around the lithic and also above it, as you can see over in that picture there. Next slide, please. Yeah, that's the one. So what we've done, these stone tools are lying scattered on the surface, thousands of them. You can literally walk out. Anybody can go there, take a lot of water if you go because it's harsh, and you can literally look down at your feet and you will find these beautiful lithics. So the question is, why are they at the surface and how long have they been there? Well, by digging pits through the sand dunes, as well as digging pits underneath the places where we excavated, we've been able to see that the lake floor sediments rise up slightly under the dunes. They rise up by about 10 or 15 centimeters. So where we found lithics beneath the dunes, we could date the sediments above and below. Outside in the open air where we did the archaeological excavations, we dated the sediments below, all using OSL. And to cut a long story short, we can bracket the age of each individual archaeological site that we excavated. In the case of this one, it falls within the window of about 84,000 years ago to 57,000 years ago, which on our hydrological model for the basin from the dated shorelines was a dry period. People were there during a dry period, but after they were there, another wet period occurred. What happened in that wet period? The rivers from the very big catchment that supplies Makgadikgadi brought more sediment in, burying the stone tools, which is evidenced by what we find underneath the dune islands. Next slide, please. And one of the important things, and this is why multidisciplinary research is important, atmospherically today, Makgadikgadi is one of the biggest sources of mineral dust into the atmosphere in the southern hemisphere. It's one of the 4 big atmospheric dust sources. Next slide. It's an incredibly dirty, dusty place to work. This map on the left here shows the trajectory of individual dust storms in southern Africa from MODIS data in a particular year, and the coloured targets are where the optical thickness of dust in the atmosphere is where the mineral concentration is greatest. And the orange spots are, the one on the right is Makadi-Kadi. The other one is Etosha, which is another big paleo lake in the system. So that basin is throwing out dust all the time every year, and that's gradually lowering the surface of the basin, exposing those stone tools that have been buried for 50 to 80,000 years. So the reason they're being revealed undisturbed, even though there's been lakes there since, is that they've been protected. And now they're being gradually unmasked every year, new sites. And the new sites we come up with have new chronologies. Next slide, please. Final thing I want to say is, how were people moving in that landscape? Well, the answer we partly answered that by looking at the material they have used to make their tools from. I said earlier that their tools are mainly made from black silkreete. About 98% of everything the Middle Stone Age tools are made from black silkreete. Silkreete is a pedogenic material. It forms through the precipitation out of silica in close to surface groundwater. And then it can form quite extensive outcrops like this. Next slide. But it can also occur in quite sort of patchy location, outcrops as well. Different forms of silkreete outcrop are shown in those top 4 photographs. Every dot on this map here is a silkreete outcrop. We sampled over 200 silkreete outcrops in the field. There are also silkreete outcrops exposed along river valleys that feed into the lake basin. A couple of examples, which are known to be Middle Stone Age quarry sites, are shown in the bottom 2 photographs. They're extraction sites where people have got material. Next slide, please. So what we wanted to know is, where had people who'd made those tools in Makadi-Kadi, where had they got the material to make those tools from? So we carried out geochemical analyses of waste material from each of our excavation sites, but also geochemical analyses of all of the silkreete locations within and around the basin that I've appeared on there. Shall I dance? Of all the outcrop locations that we sampled. And next slide please, we use ICP-MS and ICP-AES to actually characterize the immobile trace elements found within the silkretes. Next slide please. And some of the silkretes have geochemical signatures that are quite widespread in the landscape. So the slide on the image on the right shows our silkreete type 5, which is found in a whole range of different locations. And it's probably a feature from a big flood in of gentle water into the basin at some point, and then the precipitation out of the minerals. Other silkretes have much more confined geochemical signatures. They occur in patches. Here are 4 different ones shown on this slide. So it's a bit like your fingerprints. They're nearly unique. Each flood event, each groundwater movement event from which a silkreete is formed has a subtly different, particularly in terms of rare earth concentrations, a subtly different geochemical signature. Next slide, thank you. By statistically comparing the signatures of all the outcrops with the signatures from the waste flakes from the excavations, we could find where people had got the material from to make the tools. Now, why is that important if the material is available everywhere? To cut a long story short, because there isn't much time, this is one of the sites that we excavated, MAC 33, and at that site we found every black dot is a silkreete outcrop. But we found that people were not making their tools from the nearest available material. They were making their tools with silkretes that were well over 50 kilometers away in some cases. Why is that important? It suggests people were being selective. Not all silkretes are the same. Some are very friable, some fracture too easily, others it's impossible even with a hammer to break them. They were selecting materials based on their material properties, what makes the best tool. And they were carrying it with them in the landscape to make a tool when they needed it. Next slide, please. So that is important. It's important for two reasons. One is it shows that people were dynamically behaving in a dryland landscape. They didn't all run away when the climate got drier. And secondly, that back 100,000 years and slightly less, our ancestors were making decisions about where to go to hunt, but also what they needed to hunt. They were actually going to the shop, if you like, if the landscape is the shop, picking the tools that they needed and moving them with them to make a tool. They weren't just randomly acting as people, as early people without much brain capacity. They had the capacity mentally and physically to survive in a harsh desert landscape. And you'll probably ask me, where did they get their water from? Well, the evidence probably is, we haven't found it yet, but evidence from East African sites is that by this time, people were using blown out ostrich eggshells to transport water in. They would fill them up with water from sip wells and carry it with them so that they could move in dry areas. So our ancestors did not simply evolve in the wetter places of Africa before they left the continent and after they left the continent. They were surviving and innovating in the driest areas as well. You would think in a basin like Makgadikgadi that people would have been there only when the lake was full. But they were there when it was bone dry, when the climate, paleoclimate and paleoenvironmental records show that the basin was actually arid. And that is quite significant for theories of our development as a species. Next slide, please. So I won't go through that slide. I don't like slides with lots of words. But basically, the Kalahari didn't empty out 130,000 years ago. People may have dispersed from there, but plenty of evidence for remaining residual populations who were innovatively coping. And as a general lesson for all of us, it should tell us that the absence of evidence is not the evidence of absence. So much of science is dependent upon the data sets that we have. And if we haven't sampled everywhere or everything, we cannot assume that things didn't occur or hadn't happened somewhere. So sampling is very important, and a lot of fundamentally important archaeological theory is actually based on poor sampling or very taphonomically driven sampling. So we have to be careful when we make theories about where our evidence comes from. Next slide, please. And final thing, this is an image of a headline in the New York Times last week. I'm talking about the Middle Stone Age, when we evolved into our current state. There are now sites in East Africa where, for the first time, where the ancestor of Homo sapiens, Homo erectus, whom it had long been thought really survived in wet savanna conditions, there's a new paper out in PNAS that said that even Homo erectus 1 million years ago was surviving and behaving in an efficient way in extreme aridity. So we shouldn't assume that we've only developed coping strategies recently. As a species, we've developed coping strategies throughout our history, and we need to be very clever into the future as environments get more challenging because of climate change, and as there are so many more billions of us now than there were then. But as a species, if we're sensible, we have the capacity to adapt. Thank you very much.
If you have any queries, please feel free to ask.
Hello. on geomorphological process, late quaternary environmental change, climate change science, and environmental climate interactions with archaeologists, biologists, climate scientists, and other physical geographers. He has authored about 10 books and he has 200 peer-reviewed journals as well. And in 2011, David Sir was awarded the Geological Society of America Farouk Elbas Award for a body of work that has significantly enhanced desert science, and in 2019, the Royal Geographical Society's Victoria Medal as well. Sir, we hope to carry forward the valuable threads of science to the quaternary you have imparted on us. Thank you very much, sir.
Thank you.
Good afternoon. Dr. Julie Durkan is a postdoctoral researcher in the School of Geography and the Environment, specializing in luminescence dating and reconstructing quaternary environmental change. She is currently working on the Liverhume Trust funded project, Holocene Socio-Environmental Relationships in the Indus Valley with Professor David Thomas. She was awarded her PhD from Aberystwyth University, Wales, United Kingdom in 2013. Her research focused on the luminescence dating of river systems in Pakistan and relating changing fluvial activity to the collapse of the Indus civilization. Her current research interests include paleo-environmental reconstruction in low-latitude regions, reconstructing socio-environmental relationships in the late quaternary period, and the development and application of the optically stimulated luminescence dating technique. Today, her presentation on the topic, socio-environmental interactions in the Indus Valley. Welcome you, ma'am. Welcome to the session.
Okay, good morning everyone. I think we're just about the morning still. And firstly, thank you very much for the opportunity to come and talk to you today. Thank you in particular, Dr. Linto, for inviting us. And before I begin, I just want to say thank you to all the presenters so far, for both the keynote speakers and the student presenters as well, for presenting us some fantastic science. So I'm Julie Durkan. As the introduction said, I'm a geographer based at the University of Oxford and currently running the luminescence lab there. So today I'd like to talk about an ongoing project in northwest India, to take you back to India and back to the Holocene to think about landscape change in the Holocene in relation to the Indus civilization. So I feel in this setting that the Indus need no introduction really. So as you will all know, they're the largest of the Bronze Age civilizations, occupying the region of sort of northwest India and Pakistan from about 4,500 to 4,000 years ago. So this is the urban phase. They're contemporaries of the Mesopotamians and the Egyptians, and associated with advanced technologies and the building of large urban centres. But about 4,000 years ago, they collapse, if you like, or they demise. And scholars over the last 100 years or so have been seeking the reasons behind their transformation. And the reason remains today still one of the more significant unanswered questions for Old World archaeologists. And my research aims to address this from a geographical perspective. So one of the things that characterises the demise of the Indus at 4000 is a really marked movement of people in the landscape. So here we have a map of Indus settlements. So these are sites that are dated to between 4,500 to 4,000 years ago, both the black and white symbols. And you can see they're distributed broadly on the tar margin. And if you watch the change in the figure, the next figure will plot the post-urban Indus sites. So what happens after 4,000 years? And you'll see this quite stark movement in sites towards the east. Now, critically, as you'll know, the Indian summer monsoon brings precipitation from the east, and today, approximately 80% of precipitation is derived from this system. So this has led many scholars to sensibly ask whether climate changes in the past might have contributed to some of the archaeological changes which are documented. And this is a sensible question to ask if we look at climatic proxies. This is a speleothem record and a characterization of changes in Indian summer monsoon intensity from the Holocene through to about 3,500 years ago. In this record, published by Berkelhammer and colleagues in 2012, you'll see the Holocene intensification of the monsoon system from about 9,000 to 8,000 years ago, and then a de-intensification of this system. You'll also see, with the sort of punctuated spikes in the records, the superimposition of more abrupt events. And notably, about 4,000 years ago, you see this quite significant drought event, so just marked in the red there, that coincides with the transformation of the civilization, with that movement of people that we saw earlier. So it appears it is sensible to suggest climate might be a factor. If we look to regional records of climatic variability, we'll see that climate change seems to have occurred as interpreted from a variety of proxies. This is the Mwamula Cave speleothem record that I showed earlier, where you see this early Holocene peak in monsoon activity, de-intensification, and that 4,000 4Ka events. And if we look more broadly at a Chinese cave speleothem record, you'll see the same picture, that more intense monsoon, and as we move through the Holocene, de-intensification, and again, these sort of punctuated abrupt events, including that 4,000 year event. Looking at marine sediments in the Indus Delta, Stelbosser and colleagues from geochemical records was able to show decreased output of the Indus River during the urban phase, and a series, what they interpret as a series of droughts through the urban phase. And later, reinterpreting the same core, but this time using high-resolution geochemistry. Elena Geish at Cambridge looked at winter monsoon intensity as an output from the Indus River. And again, she seems this sort of same emerging picture of enhanced aridity or decreased output from the Indus through that sort of key archaeological phase. Terrestrial records show a similar story. So we've got some classic playa or dry lake records from the Rajasthan region, so more proximal to the Indus occupied area. And for example, lake level reconstruction from sediments at Didwana and Lankaransa show us relatively higher lake levels in the early Holocene, reductions as we reach 4,000 to 3,000 years ago. with Lankaransa interpreted to have dried completely from about 4,000 years ago. And again, similar sort of story if we move up towards the Indus-occupied area. Yama Dixit looking at both Lake Karsandi and Kotla Dahar, using a combination of ostracods and lake sediment analysis, again showed the same sort of picture. But people don't just live in a climate. We experience climate, but we live in a landscape. So what my research aims to do is to try and understand how these changing climatic conditions during the Holocene, both the long-term and the abrupt changes, might have impacted landscape evolution. I'm a geographer, and the geography of this region is really interesting and diverse. You don't need me to explain the geography of India to you, I'm sure, but of course we've got these highly energetic, aggradational tributaries of the Indus and the Ganges systems draining the Himalaya. We've got the Thar Desert, of course, and it's this really interesting sort of area in between these two geomorphic systems in which the... I'm echoing. Something changed? Okay, better? Okay. So it's this really interesting part of the landscape in between these two systems in which both the Indus occupy, but also this transformation occurs. If we zoom in on this area, these are the large Himalayan rivers highlighted: Ganges, Sutlej, Beas, Indus. And in this Indus area, we've got the Gagahakra channel, so draining from the east, flowing across the border towards the Indus. This river should be really important in the history of the Indus because sites are located adjacent to it. And that area of transformation that I showed you earlier, where people were moving from the west to the east, occurs along this fluvial network. So I, along with colleagues, including Dave, are seeking to reconstruct landscape change through time to try and understand what was going on here during the Holocene. Now, it's long been recognised from early remote sensing mapping work that this Gagahakra channel is complex. We see that from the work of Goes and colleagues, for example, where you see multiple tributaries and paleo channels feeding the surface channel that we see today. There we go. But the picture today is much more complicated. A colleague, Hector Arengo, based in Barcelona, has used multispectral remotely sensed imagery to map the buried fluvial network. And just on this Indian side of the border, he maps over 8,000 kilometers of buried channels. Now, crucially, we don't really have much in the way of chronology or understanding of this buried fluvial network. There have been a number of studies, a number of very good studies published, which predominantly focus on the visible Gagahakra system. But the Indus sites aren't just co-located along this along this river. So what we're seeking to do is to undertake a regional paleo-environmental reconstruction. Because if we want to understand civilization scales of change, we need to understand at least regional landscape change, rather than and using these studies, which are all very good, but tend to focus on just points in the landscape. So I'm seeking to do something that's bigger and that can connect these very important past studies together. So the aim of this work, funded by the Leverhulme Trust in the UK, as I've said, is to try and undertake systematic reconstruction across this Indus-occupied landscape. We want it to be data-driven, though, and use the geography first. So not be led by the archaeological patterns, but instead look at the landscape and use that reconstructed change to test against climate and then to test against the archaeology. Yep. And I've said that as well. So I'll be talking mostly about, we'll be talking primarily about luminescence dating today. So our aim and our methodology to undertake our reconstruction is to be guided by remotely sensed imagery of both the surface and the subsurface. Combine this with sampling sites in the environment that indicate past environmental change. So perhaps dried river channels or large dune accumulations that you can see in the photos. Sample these for sedimentology, chronology, and provenance, and use this to reconstruct the landscape. And then critically, the next step in this project is to undertake modelling. So to be able to combine these different data sets of different data types that we've got and statistically interrogate them. So we can look, for example, for leads and lags within the system. So what we've got so far is quite an extensive set of dated sites and quartz OSL ages. We have 140 luminescence ages in total, ranging from the western side of the Gagahakra in Pakistan through into India, focusing on both the Gagahakra, this main channel that's highlighted in blue, but also one of these significant Chautang or Dishravati systems to the south. So I just want to spend the next couple of minutes just giving you some highlights of results found so far. So with this extensive data set, we can ask lots of different types of questions. We can zoom in onto key archaeological sites and try and understand how particular sites may have been connected to river channels, for example. This example is one of Rakhigarhi. You'll know it as the largest urban centre in India, occupied. Sorry, almost. Thank you. Almost. So where were we? Rakhigarhi. So Rakhigarhi is the largest of the urban Indus sites in India. And I'm sorry that the figure hasn't come out very well, but Rakhigarhi is located on one of these buried river channels that Hector Arengo has identified. So questions that you might ask are, what's the relationship with those buried paleochannels and the site? And just an image to show that modern day Rakhigarhi and one of these buried channels that runs pretty much straight through it. But there is another buried channel 10 kilometers to the north. So as part of this project, we sampled intensively two 20-kilometer transects of the fluvial channel to reconstruct the past history. So the results I was initially expecting, or perhaps hoping for, was to see a nice river flowing till about 4,500 years ago. The river dries out and the site's abandoned. But of course, researchers never really like that. And instead, the story I've yielded is one of a Pleistocene history, predominantly of these channels. You can read the luminescence ages from southwest up to the northeast. And here, as you can see, there are two Holocene age samples. Instead, the rest of the very fine sands and silts date prior to 11,000 years or so ago. We've got this one site at the easterly extent of the Paleochannel, which yields an OSL age of 6.4 thousand years. But beyond that, that's about it. So really interestingly, that we see this Paleochannel abandoned prior to the establishment of Rakhigarhi site. Like I said, Rakhigarhi is 6.5 Ka. Perhaps the north yields a Holocene record that might explain a relationship between people and rivers in this part of the Indus civilization. But again, it's the same sort of story that's emerging. Again, if you look at the transect from west to east, you see that even a meter below the current surface, you're seeing OSL ages of 11.5 thousand years ago. For 7,000 years ago there, and some very fine silts, almost clays, at 5.5. But again, predominantly Pleistocene in nature. So with this large data set, that's one aspect we can start to interrogate. We can also try and look at, we can try and make a comparison between published climatic records and geoproxy or landform records in the environment. And again, sorry, my maps are coming out not very well on this screen. But we have the Lake of Karstandi in Haryana. And we were able in 2022 to sample both the fluvial channel and a dune about a kilometre, maybe less than a kilometre, from that published site. So this is Yama's work. What she sees is a large Aeolian sand accumulation at about 11,000 years ago, followed by a period of enhanced aridity till about 7,500 years ago. A return to slightly, aridity until we see a return to enhanced, interpreted enhanced wet conditions at 7,500 years ago, a drying up until 5,000 years ago, and then she sees wetness in the urban Indus phase. And these are working OSL ages, but what I see is, again, quite an old record emerging. So in the fluvial channel, we're seeing late Pleistocene activation or deposition of fluvial sites from about 4,000 to 12,000 years ago. In the dune record, we do pick up the 11 Ka event, or the date for that unit here, at depth. But we only recover very modern sediments in the upper 4 meters or so of the record. Like I said, these are OSL dates that are in progress, but again, it's just another interesting thing that you can do to try and start combining climate change and landscape response. So finally, I'm nearly there, to give you more of a regional view. We have 140 OSL ages, we have over 40 sampled sites. So now we can start asking questions more broadly about when rivers were flowing in this part of the world, when were the dunes active, and is there a relationship to the archaeology? And we've got sort of a cartoon sort of representation of the monsoon from about 20,000 years ago to the present day, with key key Indus phases indicated by the coloured bars. And just to try and give you a summary of 15 years' work in a couple of moments, if we look at the Pakistani side of the border, we can plot our OSL ages. The field symbols indicate OSL ages from river sediments, and the open symbols indicate OSL ages from dune sediments. So on the Pakistani side of the border, the picture looks relatively straightforward. We have enhanced monsoon intensity, and we have fluvial deposition from about 10,000 years ago through to about 4,000 years ago, with the episodic reactivation of the Gaga, but nothing more. And we see dune activity from about 3,000 years ago. So that looks like a nice simple picture. Maybe I should have stopped there. If we move on to the Indian side of the border and look at this area of the Gaga and associated tributaries around sort of Kalibangan area, the picture becomes muddied, for want of a better word. We see, again, fluvial deposition through during that, that enhanced monsoon period, through from 10,000 through to 5,000, but the river doesn't stop flowing. We see sort of episodic deposition through time, all the way to near present day. Interestingly though, the dunes are active as well. So we see coeval dune accumulation and river activity. And this makes perfect sense actually, because drylands aren't simple. You don't see rivers turning on, flowing, turning off, and dune systems turning on. We've got a monsoon system where intensification means enhanced precipitation, but also means enhanced aeolian activity. So this is to be expected. And finally, if we just want to complicate the picture even further, we should continue east on our journey up to Rakigari, but away from the main Gaga channel into the Chotang. And again, this is where it gets a bit more complicated and needs some more thought. But we do get the deposition of very fine fluvial sediments through the late Pleistocene, but terminating at some time around maybe 8 or 7,000 years ago, prior to the establishment of the site, and then a near absence of fluvial activity that we've sampled from about 5,000 years ago through to the present day, with dune activity in the region being sporadic. So I won't talk further about the results, because this is usually the time in the talk where I would put my climate proxies back up, show you more records, plot my OSL ages, and try and draw lines to make correlations. But the next part of the project that Dave and I are involved in is trying to better statistically interrogate these records, so we can really drill in detail to try and understand what people are doing in the landscape at different times by feeding archaeological information into a model, to understand when this fluvial network was active and not, how that might impacted people, and then finally understanding how climate may in part drive the changes that we see here. So to finish with some thoughts, we have a now ephemeral river system flowing on the northern margin of the Thar Desert, which seems to very broadly be driven by regional changes in the monsoon, but it's certainly not clear. You see coeval fluvial and aeolian accumulation, so these offer a view of sort of contemporaneous humidity and aridity through the Holocene. And as I said, drylands are complicated beasts. We see sort of spatial and temporal variability in landscape processes through the Holocene. Yep. And archaeologically speaking, I'm not an archaeologist, but many scholars have suggested that the mid-Holocene was a time offering a window of opportunity for the Indus civilization, kind of the Goldilocks idea where it wasn't too wet, it wasn't too dry, allowing this civilization to thrive. Fluvial reorganization and avulsion would likely have been really important during the Indus times, of course, and monsoon precipitation would have been key for facilitating agriculture and the establishment of civilization. But what this work is increasingly showing is we don't have this simple signature of rivers switching off at 4,500 years ago. Perhaps some of the rivers switching off earlier than that, and the Indus were making active decisions to occupy abandoned or rarely active paleochannels, providing fertile floodplains for agricultural systems. And I will leave it there. So I hope I'm within time, but thank you very much.
inversion on the lower part and maybe 9 kilo years and above